right, so the last speaker for this morning is Mr. Patrick Burkardt. He's a PhD candidate in mechanical engineering at the Aachen University in Germany. And his presentation is entitled Biohybrid Fuel Blends for Spark Ignition Engines, Design and Performance Analysis.
Okay, thanks, Thibault. Ladies and gentlemen, friends, actually, I'm not really an AI guy, so meaning it's not my core field of research, and also my experience is not that comprehensive, let's say. But anyway, I think it's an interesting topic, and it's really great to participate in this very conference. So when I prepared for this conference, I really asked myself the kind of basic question: so what is actually AI? And I came up with the idea, why not asking an AI, what is AI? So I did. And starting with this basic question about what is it, I got a pretty good answer. I will not go through it in detail, also shorten it a little bit, but I was really impressed by the condensed information in such a short answer, basically. And based on this answer, I was already able to ask a second question as a follow-up question, because I thought I already understood a part of it about the training concept of the training part of AI, let's say. So is AI actually always connected to training? And I got a positive feedback, so obviously it is. And I thought, well, let's ask something maybe more specific about a research topic I'm more familiar with, to see how good the training data actually was. So, in particular, I asked what is a pre-chamber combustion. It doesn't matter what it is for now, I just asked it. And the answer was like, okay, I would say. So basically, I got a point what pre-chamber combustion is. However, there were some weird word combinations like diesel engines and spark plug, which is kind of contradicting, but okay, no one is perfect. So while I would be able to answer this question better, I think this would definitely not the case for the next question, where I asked a little bit more about fun to create a poem about pre-chamber combustion. And actually the answer was even better than everything before, and proved that I'm not really able to do it better than the AI did. So after this not really seriously meant preparation, coming back to the title of my presentation. I want to use it to guide a little bit through the slides. I think there are some terms included that needs to be discussed or even explained. And I would like to start with the term of biohybrid fuels and the question, what is it? To explain it, I would like to shortly introduce our class of excellence, the Fuel Science Center, where this a term of biohybrid fuels was actually created. So it's one of, I think, 57 classes of excellence in Germany, funded by the German government. And this particular one, we are working on fuel science, as the name states. The goal is this overall closed carbon cycle. So we're using CO2 for the fuel design or for the fuel production, and emitting CO2 afterwards in the propulsion then again. So to make it short, biohybrid fuels are just combinations of biofuels and e-fuels. In its predecessor of FSC, it was TMFB, stands for tailor-made fuels from biomass. We just worked on biofuels, and now we also included this aspect of e-fuels, but do not consider them as two separate fuels, but combine them in biohybrid fuels. So this is basically all the magic behind the term of biohybrid fuels. Now that we have clarified this, I would like to go over to the design of the fuel. So how this was done and which particular fuel we actually got at the end. This was done basically in cooperation, or mainly it was done by our colleagues from the Process Systems Engineering, head of chairs, Professor Alexander Mitsos. They are also part of RWTH Aachen University and also part of the Fuel Science Center. And they consider a so-called integrated product and process design. So you have two parts. The first is the process design, and the basic question is here about the which production process or routes can we use or shall we use to get a most efficient fuel. There are a couple of approaches available. I prepared 3 of them for today. So the first is a so-called reaction network flux analysis, where the overall goal is to minimize the cost and the carbon loss during the fuel production. The second approach is then a process network flux analysis, where the overall goal is to minimize the cost and the CO2 emissions, or the CO2 equivalent emissions, if there's anything else emitted than CO2, then it is considered as well. And the third one is a little bit broader view, and so not only on the process flux, but also what comes before, like the supply chain, and what comes afterwards, like byproducts. I mean, fuels at the end are just molecules or a group of molecules, and they can also be used in chemical processes for as well, if applicable. For the fuels investigated here, so I will show in this presentation, we use the first 2 approaches. So this is the first part about process design. The second part is then the product design, and the core question here is about the fuel properties. We try to tailor the fuels to an engine by using the fuel properties as a first indicator, let's say. And so the question is, which properties do we need and how should they look like? There are also different approaches available. I just prepared a few of them here. So in the first step, we used this graph-based molecule generator. So the goal was to get a molecule graph or molecule structure, as can be seen on the right-hand side. Therefore, we started in a latent space by where we optimized the molecules to get these so-called molecular fingerprints. And in a following model generator model using these approaches stated here, we then got these molecular graphs. So these are still no fuel properties, obviously. So we need another step where we started then with the molecular graph. And in this graph-based neural network then, where every atom is represented as a node and every bond is represented by an edge, we then started to work on this in this end-to-end learning approach. For every atom, then its environment was learned by graph convolution. Afterwards, these environments were combined in a so-called molecular fingerprint, still not a fuel property. This was done in the last step, where we used an artificial neural network to map the molecular fingerprint to the molecular property of interest. In this particular case, the molecular property of interest are ignition quality describing parameters. So in particular, the research octane number, motor octane number, and derived cetane number. So these are just a few of fuel properties in which we are interested. I would show more later. Actually, this tool is also available online. There's a link, so you can just go to the web page and type in the smile code to get on these values for RON1 and DCN. So this is the part of the product design. And when we combine them both, we got hopefully a promising fuel candidate. So which fuels then did we actually get then? We started with a database, let's say. So those are the production routes that are generally considered in our approaches. Additionally, we consider conventional gasoline fuel. Why? If there is a product route that is less efficient than conventional gasoline, the optimizer would choose gasoline instead. This is the only reason why it is there. Based on this database, we would get a lot of fuels probably, so we have to make some constraints. Therefore, yeah, there are two, let's say, stages available. The first was developed in TMFB, so the predecessor of FSC, and the next was then in FSC developed. They are not that different, I would say. We switched from a decane number-based description to an octane number-based description, for example, and added some more constraint due to legislations or future possible legislations. Basically, in common for both is that they are suited for spark ignition engines, so not for compression ignition engines. So coming from this database and restricting it a little bit with some boundary conditions and using the before shown approaches regarding process and product design, we then actually got two promising fuel candidates, which you can see here. The first from TMFB is called EBCC, and the second one out of FSC is called KEAA. Now, you can see here their fuel properties. I also show or put ethanol and 2-butanone for comparison here. Ethanol is kind of a benchmark to beat. I know there are fuels that perform even better in spark ignition engines, but ethanol is still something we try to beat with blending. It has some extremer values like, sorry for that. Its heat of vaporization is quite high. 2-butanone, for example, has a quite high knock resistance, which does not necessarily mean that it really is that knock resistant, as we will see also in a few minutes. But in sum, I think we can classify these two fuel blends somehow in between ethanol and 2-butanol. So promising for a spark ignition engine, that's for sure. So after this design aspect and after we have found two new fuel candidates, for sure there is the final question, because we want to not only produce fuels but also burn them. So last question is about the engine performance. How did they perform in an engine? Therefore, we used one of our research engines as a single-cylinder engine, modularly designed, so we can adapt it depending on the investigation case that we want to consider. In this case, we choose a compression ratio of 16.4, which is high for a spark ignition engine. However, considering the fuel properties that were predicted, it seemed to be appropriate. Despite that, the engine is quite conventional in terms of its combustion layout, so a laterally mounted direct injector between the intake valves and a centrally located spark plug. So the results are then shown here. In the first variation, we performed a variation of the net indicated mean effective pressure, so the engine load basically. And all of these new alternative fuels performed quite good. I also showed a conventional gasoline fuel here, which is quite limited in its operating range due to its knock limitation at such a high compression ratio. The alternative fuels that we have designed, so EBCC and KEAA, performed comparable with ethanol and 2-butanone. In particular, EBCC was even able to outperform all the other candidates, which also impressed. We were also impressed by this. One reason can already be seen, but it will become more obviously later, that the combustion duration and the flame development angle is quite short, or shorter in case of EBCC than in the other cases, which means that it obviously burns quite fast. Looking in the exhaust runner and therefore in the emissions, NOx emissions are temperature driven mostly, or mainly. Meaning the lower the temperature, the lower the NOx emissions, or combustion temperature in particular. And this is still where ethanol is the best performing candidate just due to its high enthalpy of vaporization. A second variation was then performed by varying the relative FU ratio in the exhaust runner, so it was measured from exhaust gas components. And the picture regarding the indicated efficiencies is quite the same. So EBCC was already again outperforming the other candidates. It even achieved a slightly higher lean limit, so by 0.1 units. And here it also becomes now more obviously that the burn duration and the flame development angle is a little bit shorter for EBCC, which contributes to its better efficiency performance then as well. Also here, the exhaust, the emissions in the exhaust runner is still ethanol due to its higher enthalpy of vaporization has lower NOx emissions. However, in general, the NOx emissions are driven by the relative air-fuel ratio rather by the fuel itself. So if you are operating at very lean conditions, then basically every fuel achieves quite low values. So I will conclude. Biohybrid fuels we have seen, they are basically just combinations of e-fuels and biofuels defined in the Fuel Science Center. We used an integrated product and process design to develop fuels and actually got 2 promising fuel blend candidates. And lastly, we investigated them as well. And in conclusion or in summary, I think they were competitive with the combustion performance of ethanol and 2-butanone. So what's coming next? First of all, we will investigate these fuel blends also in other combustion concepts. First of all will be a pre-chamber application because it's also a core part of the FSC. And second, we will implement an engine model in the fuel design process. Why should we do this? The outstanding performance of EBCC was kind of luck, so it was really not expected. KEAA was, on the other hand, performing good, but not better than any other fuel. One reason is that we just consider the production and process aspects in the fuel design process and not their actually combustion in an engine later. So this is why this engine model shall be included, so that at the end the fuel that has the best performance in its production, in its process design and in the engine performance can then be selected and hopefully will then also perform best in the engine. One last slide, kind of a key take-home message. If you are interested in more of these topics in more detail and in a broader way, a broader range maybe, then there's also a conference you can join. It takes place yearly. It's for no participation fees, and we are happy to welcome. Thank you.
Thank you very much for the interesting talk. Sorry. I have 2 questions, quick one, on the process design and the product design. So the process design, what's the core base of it? Is it an Aspen model that looks into, catalyst reactors and up to that level of modeling?
I don't really get the question.
The process design. I mean, the initial part of your model, there is a process and there is a product.
Yeah. Right.
So the process design, what's its core? Is it a refinery model, or let's say you call it a hybrid bio-based model where it looks into combination of reactors for e-fuels and biofuels? So how do you come up with a product here? What's the process that goes into it? Yeah.
So I'm not an expert in this, but I try to answer it. Otherwise, I can also connect you with my colleagues. So basically, they are mainly considering the if you have a chain where you you have this process chain for one molecule to another and so on and so on. You just try to minimize the losses so that the fuel at the end has the highest efficiency or the lowest losses. So this is a really basic concept. I don't know if this answered the question.
And commercially viable, I mean, okay, maybe we can, if you can connect me to the maybe person. On the product design maybe. So we saw that your candidates that you came up with, they outperformed the baseline gasoline. So how do you make this correlation from fuel property, let's say good fuel properties for an engine to be running well, yeah? And you started with SI, now moving to pre-chamber. So it's still, I look into engines, I work around that engine, but it's not really straightforward what would be the perfect fuel for it from a property standpoint. So how do you come up with, from a process side, saying this is the RON that should be amon, and these, I don't know how many lists of properties you're looking at, but it's not that straightforward to come up with this cohesion. Yeah. So what's your merit function, if maybe the simple question?
So we're just considering spark ignition engines, as mentioned in this. So for sure, like research octane number should as high as possible. Yeah. So if a fuel has really a very high research octane number, this is first of all good. No? Enthalpy vaporization is also great in terms of knock resistance. It could lead to some problems in the cold start behavior, maybe. Lower heating value is another point that we are really looking on. So it should be also as high as possible so that we do not have to carry a lot of fuel with us. But at the end, it's like, you have to consider the fuels, or you have to evaluate the fuels a little bit one by one and see which one is the best. So you cannot really say, okay, this is now definitely better than the other, because all these properties are influencing different values, like efficiency and exhaust gas emissions are often like trade-offs. And so you have to just evaluate it, for each fuel independently and step by step. So this is basically how we do it now. Maybe it will change.
Thank you.
More questions for Patrick?
Hi, thanks. Jamie Turner. Yeah, great talk. Really interesting results. The EBCC is obviously pretty good fuel, almost as good as methanol, I should imagine. Have you run the engine on methanol in the same conditions?
We did, but I know we know it. Beating methanol is like a whole other story. In its engine performance, like 16.4 in the compression ratio is maybe not high enough. We did, it would be higher than EBCC. Yeah.
So I did notice it's got 2% methanol in the EBCC.
Yeah, right.
So was the EBCC designed to comply with European legislation? Because obviously it's 3% is the max. 3% methanol is the maximum, and then there's the oxygenate limit. So were those?
The oxygen is, you're right, the oxygen fraction is basically a limitation factor. I'm not sure. I thought it's like 5 mass percent, maybe just in free volume percent, something like this. We considered some possible future legislation to go up like 8% or something like this to really, otherwise we would really restrict ourselves to find new fuels. So we, widened it a little bit, and so this is also the reason it was done for KEAA. So that's the reason why methanol came in there and was not part in EBCC, I think.
Right.
At least this is what I have in mind.
Okay. So and final question: the only reason why you limited the latent heat, was that really just a cold start consideration? Because pretty much that's you definitely have it if you could sustain it.
The cold start was the question, right?
Yeah, you mentioned the latent heat being a problem for cold start.
Yeah.
Was that really the only reason for limiting the latent heat?
This, and we've seen in some past experiments that the HC emissions were also quite high in catalyst heating operation points, especially for ethanol, I think it was. So this was another reason, but actually these two. So cold start behavior and HC emissions then, because of the wall wetting when it's too cold.
Okay, thank you.
All right, so I think it's pretty good timing to stop here. Let's thank Patrick again. All right, so it's